Yeah, I can see it. Okay. So should we start?
Sure.
Yes.
Okay. So
We
good
are ready
afternoon.
now.
Yes. Good afternoon, everyone, and welcome all to the lecture series on atmospheric dynamics and its applications to climate sciences, which is hosted by SAMA and SPPU together. So before today's lecture will be delivered, which is lecture number 7, will be delivered by Dr. Abhijit Sarkar, a scientist of NCMRWF, and he's retired from NCMRWF. But before we proceed for that lecture, I would request Dr. Kyamo Wu to please give the welcome address, who is DG DHM Myanmar. Sir, please.
Thank you. Thank you. Excellency, distinguished guests, ladies and gentlemen, and all participants. I am delighted and honored to welcome all of you to the lecture series on atmospheric dynamics. Firstly, I would like to express my sincere thanks to SAMA and SAMA-SPPU, fully owned University, India, for organizing the important lecture series and for providing the necessary arrangement for the lecture and also the technical guideline. I also would like to thank all participants and Dr. Abhijit, Sarkar, NCMRWF, this lecture series program. Nowadays, the vulnerability to disaster is increasing more than ever. We cannot prevent those hazards from happening, but we can reduce the impact of disaster by good preparedness. Here, it is obvious that certain at the lecture series is one of the precaution measures for reducing of the disaster impact enhanced by climate change. After completing the lecture series, I do expect that participants will be equipped with knowledge and wisdom for relevant approach method and tools for risk and vulnerability adaptation, assessment for formulated and implementation of an early warning, and also having ability to identify regional issue and approach on climate change intervention. I hope this lecture series will also granting an opportunity to bring to a productive dialogue between student and teacher about the theoretical and practical aspect related to meteorology. I recognize that the point of this lecture series is made out of the core material to share, enhance, and develop best practice for implementing national meteorological services. I hope the participants will actively contribute and share knowledge and experience of the individual and identify the needs and come up with better solution for meeting the objective of this lecture series. Finally, I would like to be sincerely thanks for the esteemed member of the SAMA and Bonn University and Dr. Abhijit Sarkar for successful of the today lecture. I wish all of you have comfortable and pleasant learning of this lecture series with good health and happiness. Thank you very much for your kind attention.
Thank you, sir. And now I would request Dr. Mili Ghosh Nilala from BIT Mesra to please introduce our today's speaker. I'll share the screen. Yeah, I think.
Yeah, it is visible. Yeah. Thank you, ma'am. And it's my pleasure to introduce Dr. Abhijit Sarkar, sir. Dr. Abhijit Sarkar has served National Center for Medium Range Weather Forecasting, Ministry of Earth Science, Government of India as scientist staff. His areas of research include numerical weather prediction, modeling, and ensemble forecasting. He took lead role in operational implementation of the following: Unified model-based global ensemble prediction system of 33 km and its upgradation up to 12 km resolution. then regional ensemble prediction system of 4 kilometer resolution, and various probabilistic forecast products. He has done his MSc Physics from University of Calcutta, MTech in Atmospheric Science and Technology from IIT Kharagpur, and completed his PhD in Atmospheric Science from IIT Kharagpur. Dr. Sarkar has served the prestigious position of scientist in charge of BCWC between 2020 and 2023. He played key role for NCMRWF in doubling as Bay of Bengal Initiative for Multi-Sectoral Technical and Economic Cooperation Center for Weather and Climate. He has published several research articles in journals of national and international repute. He has been awarded with Certificate of Merit by the Ministry of Earth Science, Government of India, in the year 2016 for his extraordinary contribution in the field of atmospheric sciences. Thanks a lot, sir. We welcome you, sir.
Thank you.
Thank you, sir. And now I request you to please share your
Okay.
screen.
Okay.
Participants, we also request you to please write your questions in the Q&A box, and the attendance link will be shared shortly.
Is it visible?
Yes, sir.
Okay. At the outset, I want to thank SAMA and the Savitribai Phule University and all the organizing committee, and my friend Dr. Sagata, Dr. Tyagi sir, Dr. Someswar sir. And today, the topics what I will cover, that is hydrostatic balance, geopotential, use of pressure as vertical coordinate, and ageostrophic wind, and horizontal acceleration. And in absence of acceleration in the atmosphere, or whether if atmosphere is static or if it is in uniform motion, vertical force on the air, so we can tell that there is no vertical acceleration. So then, and we know that pressure, it is nothing but the weight of the atmosphere, weight of the atmospheric column over a point per unit area. So if we take a piece of that atmospheric column, so that is that is denoted by this air cylinder. So the pressure, the force due to pressure from the top, so that will be equal to P plus delta P delta A. If we consider that P plus delta P, so that is the pressure from the top, and from the below, if pressure is P delta A, so then the downward force will be at the top surface, that is will be equal to Ft is equal to minus P plus delta P delta A. And the upward force, so that will be P delta A at the top, at the bottom surface. So that is at the bottom surface. And there is another force, that is the gravity. So that is acting vertically downward. So this gravitational force will be m into g, and m is equal to rho into delta A into delta Z. Rho is the density, delta A is its area, cross-sectional area, and delta Z is the thickness. So in the vertical direction, these three forces will balance each other, then only we will get that acceleration 0. So that's what we have done here in this equation. Fb plus Ft plus Fg is equal to 0. And then we are substituting these values of Fv and Ft. So then we can see that this minus P delta A and plus P delta A, they are cancelled out. So these delta P and delta A, and in FGO term also there is a delta A. So that term is also gone. So it remains with delta P plus G rho delta Z, that is equal to 0. And then from here we are getting delta P is equal to minus 0 delta Z. Now if this thickness we take it is very thin, delta Z tends to 0. So then we can write delta P as del P del Z delta Z. And then we are putting this value of delta P in this equation, and then we get that del P del Z is equal to minus rho G. So this equation is called the hydrostatic equation, and we call that atmosphere is in hydrostatic balance. Although we are telling that if the atmosphere is static, so then there will be no vertical motion, and then the atmosphere will be in hydrostatic balance. But even when the air in motion in atmosphere, so then also that hydrostatic balance is a very good approximation. That we will see later. And the negative sign here, so it indicates that delta P, that P decreases with Z. And then equation 1 can also be written as minus 1 by rho delta P del P del Z is equal to G. And then left hand side we can write it is the vertical pressure gradient force. So this minus 1 by rho del P del Z is equal to vertical pressure gradient force. And when the atmosphere is in hydrostatic balance, then the gravitational force and the vertical pressure gradient force, they will be in balance. Now this condition is a very good, this hydrostatic balance condition is very good approximation in the atmosphere, except for very intense small scale disturbances like tornadoes. So otherwise it is very good approximation. So with the help of scale analysis, we can show it later. Next, we are coming to geopotential. Now we know the gravitational force is a conservative force field, and it acts the vertically downward direction. So since the force field is conservative, so we can express this force field as the gradient of some scalar function. And that scalar function, we are calling it geopotential. So here we are writing this G is equal to minus GK, K unit vector, it is minus K, means it is vertically downward, and that is equal to minus grad phi. So this is minus grad phi. So grad phi, this gradient is a vector which direction is perpendicular to the surface, that is phi is equal to constant. So it is normal to the surface, phi is equal to constant, and in the increasing direction of phi. Since the minus sign is there, so that means, so it is in the decreasing direction of phi. This phi is called geopotential. Now since it has only k component, so grad phi, if we expand in Cartesian coordinate system, so we can write del phi del xi plus del phi del yj plus del phi del zk, and we know it has only k component, so other components vanish, so we can equate that del d phi dz is equal to g. So phi is only function of z now. So then we get d phi is equal to g dz. Now in SI system, its unit is meter square per second square. And as I told that since this direction of minus grad phi, it is perpendicular normal to the surface, phi is equal to constant. So we can tell that K is normal to the equipotential surface. Phi is equal to constant surface means equipotential surface. Now let us integrate this equation 3. So if we integrate this equation 3 from mean sea level, which we will consider at z is equal to 0, and to some height z is equal to z, so then we get that phi is equal to 0 to z g dz. Now g is a force. Now dj is the displacement. So this is the work done. So this we can tell that phi, we can tell it is the potential energy of unit mass, because we have divided by m. So we can tell that phi is the potential energy per unit mass when lifted from mean sea level to a height against the force of the gravity or gravitational force. And the gravitational force is acts always normal to the constant phi surface or geopotential surface. But we cannot tell the same is true for z is equal to constant surface, because g is not everywhere same. So if g is not everywhere same, so there's an integration 0 to z g dz that also will not be the same everywhere. So a constant geopotential surface is not the constant z surface. Now, since g is equal to 9.8 meter per second square, so then geopotential at 1 meter above mean sea level, so that will be about 9.8 meter square per second square, because it is, we can multiply g into z. So numerically, it is about 9.8 times larger than the geometric height. So just to make it very close to this geometric height, so we can divide it by 9.8 and that specific energy which we will get, so that we can call geopotential height, and which will be expressed in geopotential meter. So a unit of geopotential called the geopotential meter is defined as H is equal to 1 by 9.8 0 to z g dz. Why we have taken here 9.8? Because it is the average average value of the acceleration due to gravity at mean sea level. Now, this geopotential meter is the unit of a specific energy. It is not the measure of this geometric height, but it is very close to the value of the geometric height. Now, if we now let us remember this, that hydrostatic equation, that is del P del Z is equal to minus rho G. So if we use this in place of rho, this P by RT from ideal gas law, so then we get d del P del Z is equal to minus PG by RT. Because in atmospheric science, in meteorology, it is very difficult to always find out rho. So we try to avoid the use of this density, and we generally substitute the density with other terms. So it is minus Pg by RT. So is equal to minus. So this, if we want to use that gas constant for dry air, so then we should use the virtual temperature in place of temperature. So then minus Pg by RdTV. So then we will get the change of geopotential height because of the change in geometric height dz. So that we will get minus RdTV dP by P. Now we can integrate it from P1 to P2. And so that phi will be changed from phi1 to phi2. Here P2 is our upper level, pressure level, and P1 is the lower pressure level. So after integrating this, so we get phi2 minus phi1 is equal to minus Rd integration P1 to P2 TV d log P. And we know that phi is equal to G0 Z. So substituting that, we get that the thickness of the two layers bounded at the upper side by P2 and below by P1. So that will be equal to minus Rd by G0 TV d log P. So from here we can see that the thickness, it is proportional to the temperature of the layer. So now this TV, we can take outside this average TV. So then the average TV, I am just telling, I am not written here, average TV will be equal to average TV will be equal to integration P1 to P2 TV d log P divided by integration P1 to P2 d log P. So if we bring out outside here, so then we will get RD average TV divided by G0 integration P1 to P2 D log P. And then again D log P, we can integrate it. And then we can get that log P2 by P1. So with this knowledge of hydrostatic equation and geopotential, so we will move forward to check these momentum equations. Now, when atmospheric is in motion, and then we will get the three momentum equations, one along x-axis, y-axis, and then along z-axis. Now, these three equations, momentum equations, in our previous lectures, we have seen they are in these forms. And these this uv tan phi by a, that the terms which are consisting of 1 by a, so these are called curvature terms. And then this term is the pressure gradient term, and this is also pressure gradient term, and this is Coriolis force term, and this G is gravity term. So here I must say that the centrifugal force term is included within this G. Actually, we can call it is G effective. Now, we have seen our previous lectures also that we did scale analysis to see that which terms are important and which terms can be neglected for the mid-latitude synoptic scale system. So just I am recapitulating this one. We can see that for a mid-latitude synoptic scale system, so these two terms, that pressure gradient, horizontal pressure gradient term or in the x direction, and these Coriolis force terms, so they are the largest two terms. And this next large term is that acceleration term. So acceleration term is one order less than the pressure gradient force term and the Coriolis force term. So after scale analysis, we can neglect these other terms, keeping these pressure gradient force term and these Coriolis force term and the acceleration term. And for y, in the y component also the same thing. So this pressure gradient force term, so that is of the order of 10 to the power minus 3, and this Coriolis force term is also 10 to the power minus 3. Acceleration term is 10 to the power minus 4. So if we retain only this largest magnitude terms, so then we can get left side, it is 0. We are neglecting that acceleration. And then we can get minus 1 by rho del p del x plus v. And for this y equation, we are getting minus 1 by rho del p del y minus fu. This f is the Coriolis parameter, and it is given by 2 omega sine phi. So what we can see here, that if we are neglecting this acceleration term because it is smaller, so then this motion is non-accelerated. And motion is non-accelerated means, so the Coriolis force term and the pressure gradient term, they are balancing each other. So from these two equations, 4 and 5, we can write, if we tell that they exactly balance each other, so then that velocity, that wind, that what we will get, so that we will call geostrophic wind. And then geostrophic wind we can express by Vg and Ug. So from this equation, if this Coriolis force term exactly balances this pressure gradient force term, so we can write Fvg is equal to 1 by rho del p del x, and Fug is equal to minus 1 by rho del p del y. And combining this in vectorial form, we can write is Vg is equal to k cross 1 by rho f grad p. This grad p, so that is equal to del p del x I plus del P del Y J. So now grad P, so that is del P del X I plus del P del Y J, and Vg, that is equal to Ugj plus Vgj. So if we take cross product K cross I, so we will get J. So what we will get, that 1 by rho F, so del P del X, so that is equal to Vg, and minus 1 by rho F del P del Y I, so that is equal to Ug. So that's what we got here. So Ug is equal to minus 1 by rho F del P del Y, and Vg is equal to 1 by rho F del P del X. Now Rossby number is the ratio of the acceleration term to the Coriolis force term. So that we get that U by F naught L. And if Rossby number is that smaller the Rossby number, so the larger is the chance of validity of the geostrophic approximation. And in the mean latitude, the Rossby number order will be at the order of 0.1, and in tropics it is at the order of 1. So it is mid latitude at higher latitude, because if will be large, so Coriolis force will be large. So at higher latitude, that the geostrophic approximation is more valid than the tropical region. And we can see that as the wind speed increases, that because it is proportional to V, so if 1 minute, okay, so it is FVG. So as wind speed increases, so then that geostrophic force also, Coriolis force also will increase. So we can think of like this, that we can see here, let us suppose this is the X direction, and there in the Y direction there is some pressure gradient, and pressure gradient force acts from the higher pressure to lower pressure. So under the influence of this pressure gradient force, so in an air parcel, it will start moving toward from higher pressure to lower pressure. So as it starts move, so the geostrophic Coriolis force, it will turn it right in the northern hemisphere. So it is turned right, but at the same time it is accelerated. So its wind speed increases and it is turned right. So till it goes parallel to the isobaric lines. So when it moves parallel to the isobaric line, the pressure gradient force acts to the left, and this Coriolis force acts to the right. They balances each other, and we will not get any acceleration. So the motion will be uniform. So geostrophic wind is parallel to the isobars with low pressure at the left in the northern hemisphere. And geostrophic equation does not involve time variation of the horizontal fluid velocity and cannot be used to predict the evolution of the flow with time. So from geostrophic equation, we cannot use for weather prediction. So it is there, the time is not involved here. And knowledge of pressure distribution determines the geostrophic flow. So here we can see that the geostrophic flow we can get only from the knowledge of the pressure gradient force. There is no time dependence involved, and knowledge of pressure distribution determines the geostrophic wind. For synoptic scale flow at mid latitude, that approximates 2 horizontal wind velocity to 10 to 15%, because practically the real wind will not be geostrophic. There will be some curvature, and in the lower troposphere there will be frictional force also. So equation is valid at high altitude and for straight isobars, because that if the isobars are curved, so then the effect of Coriolis force also will come. And if If it is at lower altitude, there will be frictional force also come. So then it will not be only two-way balance. Then we come to the vertical momentum equation. If we do scale analysis over this vertical momentum equation, so we will see that the vertical acceleration is very, very less compared to the two forces, that is the vertical pressure gradient force and this gravitational force. So this vertical acceleration term is very, very small. So since it is very, very small, it is the small difference between these two large numbers. So there will be a lot of error. So if we want to calculate this vertical velocity, we want to or use it in as a prognostic equation for vertical velocity. So the lot of error will be introduced because it is the difference between the two large numbers. So this is order of 10. This is also order of 10, but here it is 10 to the power minus 7. So large error will be introduced. So we are retaining only this term, that is the vertical pressure gradient force term and this gravitational force term. So we get, so then 0 is equal to minus 1 by rho del dp dz plus g. So vertical component of pressure gradient force and the gravity are in approximate, sorry, it will be hydrostatic balance. Sorry, there is a mistake, it will be hydrostatic balance. So that's what we can see, that in that hydrostatic, in this vertical momentum equation, in for mid-latitude synoptic scale system, after the scale analysis, that vertical velocity is not there in the equation. So we cannot determine vertical velocity if we use this that approximate hydrostatic approximation. So vertical velocity, then we have to in the particularly we have to calculate from some other equation. In modeling, we calculate this vertical velocity when we take this hydrostatic approximation from the continuity equation. So continuity equation provides us the this vertical velocity. Now, if the atmosphere we assume incompressible, so then we'll get del dot v is equal to 0. V means velocity. So the which has three components, that is u, v, and w. So del u del x plus del v del y plus del w del z will be equal to 0. From there we can find out w. Now, since pressure in a hydrostatic atmosphere, so the pressure is a monotonic function of z. So it has a monotonic relationship with height. So so then we can use the pressure as a vertical coordinate in place of z, in place of height. So one advantage is that equations, all these equations will become simpler, and that another practical advantage is that most observations are taken in the constant pressure surfaces. So to implement the observations for the study, so that will be easier if we use this vertical coordinate system. So now here, when you will pressure as the vertical coordinate system, so then z will become our dependent variable. Now we will try to write these horizontal pressure gradient force terms in the isobaric coordinates or vertical pressure coordinate system. So this way we will proceed. So let us take this is as x-axis and this is as z-axis. We are taking only the x-axis. We are now ignoring this y and z-axis. And suppose this is a constant pressure surface. This is denoted by P naught, and this is constant. Another pressure surface that is denoted by P naught plus delta P. Now, if we go from B to A, the pressure change will experience, the same pressure change we will experience if we go from B to C. So this left-hand side term, it physically we can understand this equation in this way. So left-hand side of this equation, it gives the rate of change of the pressure if we go from A to B, or if we travel this much distance at constant Z along x-axis. So this will be the rate of change of pressure. And this rate of change of pressure, if we multiply by delta x, that is the distance traveled, so that will give us the total pressure change. Okay, so in this direction also, if we go from B to C, so that then we will get the total pressure change, that is P naught plus delta P minus P naught. So in this Z direction, the rate of change of pressure will be the P naught delta P minus P0 by delta Z. Now, that is the rate of change of pressure in this Z direction. If we multiply with delta Z, so then you will get the total pressure change. So that means this is this P0 delta P plus minus P0 divided by delta Z. That is the rate of change of pressure with distance, with height, multiplied by delta Z. So that will be the total pressure change. The same total pressure change occurs in this direction also. So the same thing we can write, divided by the distance traversed, that is delta x. So that is the total pressure change in the x direction. So that's how we can explain this equation. Now in the limit delta z tends to 0, we can write this left hand side, this P naught plus delta P minus P naught upon delta z is equal to minus del P del z. Now here minus sign appears because as we go up, our pressure decreases. So we can write, taking the limit delta x delta z tends to 0, del phi del x z is equal to minus del phi del z x, del z del x. Here it was delta z delta x, so del z del x at constant phi. Now we are assuming that atmosphere is hydrostatic. So using hydrostatic equation, we can write del P del Z at constant x. So that will be equal to minus rho g. So del P del x Z is equal to, we are substituting this. Here. It is minus rho g. So this minus minus cancels. So then rho g into del Z del x. So minus 1 by rho. Here we are bringing minus and dividing by rho. Del phi del z is equal to minus g del z del x at constant p. And we have seen in the first part of this lecture, so that g del z is equal to del phi. So that is from the definition of the geopotential. So we get minus del phi del x p. And similarly, we can write for y component of pressure gradient force minus 1 by rho del p del y z. So is equal to minus del phi del y p. So we can see that in these two equations, if we write in pressure coordinate system, so the pressure gradient force is represented by the geopotential gradient. And this geopotential gradient term, so it does not have any rho. So that is a clear advantage. So then so here we can tell that so that okay that we will tell later. So the horizontal momentum equation in isobaric coordinate system, so that we are now coming from z this xyz coordinate to p coordinate. So from height coordinate to pressure coordinate. So if we write and if we retain the horizontal acceleration term, so then we can write du dt is equal to minus, this is the in place of pressure gradient force term, minus 1 by rho del p del x. So in place of that, we are writing minus del phi del x at p plus fv. And for the y component of momentum, so dv dt is equal to minus del phi del y p minus fu. And again, combining this, we can write dv dt is equal to minus f k cross v minus grad phi phi, where grad phi phi is equal to del phi del x I plus del phi del x I and del y j at for constant p. And this d dt, this total derivative term, see this total derivative term also now, since z is our dependent variable and p is now our independent variable, so we can write d dt is equal to del t plus d dx del x d dy del y dp dt del p. So this dp dt, so this is expressed by omega. So this is called that pressure velocity. So PS omega is equal to dp dt. So now previously in the height coordinate, when height was used as the coordinate in the coordinate system, so then w was our vertical velocity. So now omega will be used as vertical velocity. But since for upward motion, so p decreases, so we'll get that omega will be less than 0 because omega is equal to dp dt. So omega is less than 0 for upward motion, and for downward motion, omega is greater than 0. And then geostrophic relationship will also change. So that will become f k cross vg is equal to minus grad phi phi. And if we take cross product with k, so then on both sides, so then we get, so it is the back cab rule. So a cross b cross c is equal to b a dot c minus c a dot b. So that is equal to minus vg. So from there, using this, we can write that vg is equal to 1 by f k cross grad phi phi. So here the main advantage is that in this geostrophic equation, so the rho will not appear. So only the geopotential gradient from will determine what will be the geostrophic wind. So at different pressure levels, so that rho will change. So when you will use the height coordinate system, so in the vertical direction, the change of rho is significant. So at different vertical levels, we will see different geostrophic wind for the same pressure gradient force, because at different vertical levels, rho will change. But here rho does not appear. So in different vertical levels also, you will get the geostrophic wind same for the same geopotential gradient. We are taking one example. This is one 500 millibar. This is one 500 millibar chart that is generated every day in NCMRWF. This is that just analysis chart, and this pressure level for this is 500 HPA, and here these red contours, so you can see, so these are the geopotential in geopotential meter. So they are geopotential meter. If we concentrate on the right side in the right border, we can see here these geopotential isolines. So they are straight parallel. So we can use that geostrophic approximations here to find out the wind velocity. And just it is one approximated, it is one estimate, it is not accurate. So just I wanted to show that how we can find out that wind speed from this geopotential gradient. So now we can see, if we see here, the contour interval is 40 GPM. So here it is written, it is in geopotential meter. So contour interval is that interval between the consecutive contours. So that is 40 GPM. and nearly the separation, angular separation between them is about 1 degree. So if we talk about at 30-degree latitude, so this is 30-degree north, at 30-degree north latitude, so then we can calculate at this point what will be the wind speed. From this chart is showing that wind speed is greater than 30 meter per second. It is greater than maybe somewhere, maybe 40, around 40, 45. So let us calculate it. So we can calculate it. So this is delta theta, that is the angular separation, that is 1 degree. If we call it is 1 degree, so 1 degree is equal to this much radian. So this is pi divided by 180. So this much radian. So there delta y, so that will be equal to a into delta theta. We are neglecting that height of this level from the Earth's surface. We are taking this Earth's radius as their radius. So a into delta theta will give us delta y. That is the spatial separation between these two contours. So this geopotential gradient will be delta phi upon delta y. So that will be 40 into 9.8 divided by 11.16 into 10 to the power 4, this much. So that we will get 351.2 into 21 minus 5 meter per second square, I think. Okay. And then this phi f, here I cannot see it. Okay. So this at 30-degree latitude, f is equal to 2 omega sine 30 degrees. So this is 1 by 2 and these 2 cancels. So it is the value of omega, that angular speed of rotation of Earth. So that is this much second per second. And so from there, we can find out that u is equal to 1 by f del phi del y. So we can find out that it is the west. This is now here we can see that this is decreasing. So it will be in this direction. So U will be equal to 48.17 meter per second. So this way one can find out that wind speed from the geopotential gradient without knowing the density at that level. Next, we will discuss about geostrophic wind and horizontal acceleration. Although geostrophic wind is good approximation in this higher latitude, at higher latitude or in mid latitude or extratropics, but wind is always not geostrophic. It is a good approximation. I have told before that it is about 10 to 5%. Only the error is about 10 to 15%. But it is not always true that that wind will be geostrophic, because there may be curvature effect, and slightly lower layer there will be frictional force. So and so that wind always will not be geostrophic, but geostrophic part will be the major part. So that wind, we can tell it is the it will have both the ageostrophic component and the geostrophic component. So the ageostrophic flow is the departure from the geostrophic flow. So that's why said the real wind is expressed as V. So V is expressed as the Vg plus Va. So here Vg is large compared to Va. Va is small part, but Va plays important role in calculating. Va plays main role in determining the wind speed, or it plays the main role in creating the weather. Because if the wind is always geostrophic, so there will be no change, there will be no divergence, no convergence. If of course if we consider f is equal to constant, there will be no divergence and no convergence. And the divergence and convergence is because of this ageostrophic part. So ageostrophic part takes the it has the major role in creating weather and this weather prediction becomes important because of this ageostrophic part. So when this wind is not geostrophic, so then we have to retain the horizontal momentum, horizontal acceleration term. So we can retain this horizontal acceleration term here. So this dv dt is the horizontal acceleration. So this is equal to, as I wrote before, that this is the Coriolis force term and this is the pressure gradient force term. But we know that geostrophic part will exactly balance that pressure gradient force term. So we are separating the geostrophic, this V, we are writing Vg plus Va, and we are separating this geostrophic, and then that is balancing this pressure gradient force term. So we are Fk cross Vg is equal to minus 1 by rho grad P we are writing. And so that equation 16 becomes the dv dt is equal to minus Fk cross Va. So this is the equation which is, this is the relationship between the real wind acceleration of the real wind and the ageostrophic wind. Now we are taking both side cross product with k, so it is taking k cross on both side. So then we get Va is equal to 1 by F k cross dv dt. So now we are taking one assumption that dVA dt, it is very, very less compared to dVg dt, because we are telling that the geostrophic part is the major part. So then this equation becomes Va is equal to 1 by F k cross dVg dt. Now we are splitting this total derivative into the local derivative and the advection terms. So this becomes del Vg del t plus 1 by Fk cross. Now this is the advective term, and the term with advective horizontal advective term, and this is this term as with involving W. So this we call advective term and this we call convective term. So these three terms, one is Isobaric component. So I will tell soon why it is called so, and then advective component, and then it is convective component. Now all three components, let us see what are these. So maybe I will discuss only these two components, and these third components, for third component I have given some homework. So first let us discuss this isobaric component. Now the VISA, so that is equal to this del Vg del T term. So this del Vg del T, we are writing the expression of Vg here. We are writing expression of Vg here. And then we get, assuming rho and F constant, rho and F, it comes out. And then if we do this, from this, we will get del T of grad P. Okay, so k cross grad P. Before we have done this many times before. So it is minus 1 by rho F square del T grad P. Now we are interchanging the space derivative and time derivative. So then we get minus 1 by rho F square. So gradient of del P del T. Now del P del T is the pressure tendency. So it is the gradient of local pressure tendency. So gradient of local pressure tendency means, so this VISA, it will work towards the negative gradient of local pressure tendency. So that means it will act towards that direction, in which direction the pressure will decrease. Pressure will fall more rapidly than, or pressure will fall more rapidly than from where the wind is flowing. Okay, or we can tell in this way, the wind flows perpendicular to the isobars. Isobars means the lines of constant pressure tendency, and from regions of pressure rises to regions of pressure falls. So it will flow from this positive pressure tendency to comparatively less positive pressure tendency, or positive pressure tendency to negative pressure tendency. So regions of strong pressure rises to regions of weak pressure rises, or regions of weak pressure falls to regions of strong pressure falls. So now the horizontal, if we take the horizontal divergence of this, so then what we get? So we get negative. It is minus 1 by rho f square del dot del p del t, or we are getting a negative sign. So that means it is converging. So here pressure rises, the wind will flow from the region where the pressure tendency is positive to the region where the pressure tendency is negative, and it will converge. So this convergence is shown by this negative sign del dot VISA. We are getting negative. Now let us discuss about the advective component. So advective component is 1 by f k cross. So we are expanding this one. So v dot del, it means here I component, it will be u dot del del x, u del del x plus v del del y. And for j component, it will be u del del x plus v del del y of vg, and here it will be ag. If you expand this, you will get this one. Now we are considering one confluent flow. So means it is a westerly flow. This side it is west, this side it is east. So wind is westerly, and here this pressure gradient, these isobars are they are confluent pressure lines, isobars. So that means here pressure gradient force is low, here the pressure gradient force is high. And since here pressure gradient force is low, so then the geostrophic wind or speed also will be less, and here the geostrophic wind speed will be more. So here UG is positive westerly, but here UG is much more stronger than here, or we can tell that UG is increasing with X. So we are getting U greater than 0, del UG del X, that is also greater than 0 because UG increases with X. So we are getting U del UG del X, that is also greater than 0. Del U del UG del X, it is greater than 0. So when you will take that advective component, that K cross, this is K cross U del UG del X, when you will do this K cross I, so then I will get J, so which will point to the north. K cross I will give us J, so that will point towards the north. So this advective component will give us north, and this U del UG del X, so that is towards, this is towards east. So if we take the cross product, we are getting north. So our VG, so that is westerly, so that is east, and our VAD, so that is towards north, so that is towards north. So real wind, it turns to the left, it turns to the left. And dVdt, we will get from here dVdt. If we go to the previous page, we will get dVdt. We can get dVdt. dVdt is equal to minus Fk cross Va. So from this equation, we can get the dVdt will be in this direction, and it will be positive. So geostrophic wind speeds up and it turns left. That again, this advective component, another example we can take for, we can discuss for a trough, base of the trough. So here, this is one isobar, this is another isobar, that this is west, and wind is here, the trough, it is counterclockwise, so it is in this direction. So since these have negative that y component, and this negative y component, it is becoming 0, and then it is becoming positive. So here we can write it is Vg less than 0, and here it is Vg greater than 0. And wind is here also, every place it is westerly, so u is greater than 0, so u westerly. And since Vg is increasing with x, so we can write del Vg del x is greater than 0, so it is increasing towards east. So then u del Vg del x, it is greater than 0. And so what we get? So u del Vg del x, it is greater than 0, and it points north. So we get u del Vg del x, it is points north. We are taking cross product k cross this, so we are getting in the negative direction. So our that ageostrophic component, so that will be in the negative direction. So then it will be retarded. The geostrophic wind originally it is in the east direction, so now it will be retarded. So real wind is slower than the geostrophic wind at the base of the trough, so the wind will be subgeostrophic. And this acceleration, from that again that relationship, we will get that acceleration, it will be pointed towards north, so acceleration is towards the center. So we are getting this. So in gradient flow also we have seen that this geostrophic wind is it will be this wind, actual wind is subgeostrophic. So with the help of this ageostrophic flow, we can explain the same thing. And often we have we know that at that jet core, or this jet streak, this right side, that entry point right side and the exit point left side, there is that in the below level there is convergence, and it's the same thing we can explain with the help of ageostrophic wind. So from this this equation, dv dt is equal to minus fk cross va. So we can just split into the components. So we get du dt is equal to fva. So now if we take this equation, du dt is equal to fva, so we know the maximum acceleration is at the axis. So here our va will be very large, and then both at the right side and also in the left side, the entrance, because it is westerly jet entrance, that it will be less. So in this region there is divergence, and in this region there is convergence. The same thing that we can see at the exit point also here, because of the same reason. So we'll get at this right side it is convergence, and left side it is divergence. So below, at the upper level, divergence means in below it will be convergence, and so enhanced upward motion occurs in the right entrance, means at this region, and left exit in this region of jet streaks. So maximum in the jet stream wind speeds. So this convective part I have not discussed. I have given as homework, and these are the references I have used. And thank you.
Thank you, sir. We will be going shortly to the question answer session.
Yeah.
But before that, we will have a photo session. So I request everyone to please switch on their cameras. Sir, and I also request if you can unshare the...
Yeah. I'm stopping it. Yeah.
So Tyagi sir, Dr. Mohan, Ashwin, Dr. Divya. Dr. Divya. Yeah. Vishal, Tyagi sir. Ashwin, please take pictures. Yeah, Tagi sir is also here. Brunal. Yeah. So we have taken some. Now I request Dr. Swagata to please conduct the question and answer session.
Thank you, Dr. Rohini. Thanks, Abhijit, for the nice lecture. So there are few questions currently. I think when time proceeds, question also increases. The first question I took them from Mayank Pandey. If Earth is assumed to be perfect sphere, then will the geopotential height be equal to actual height of an air parcel?
Yes, it will be, because this geopotential height and geometric height, they are different because of the at different places G is different on the Earth's surface, and that is mainly because of the surface of the Earth, shape of the surface of the Earth. So it will be same.
Okay, can you suggest a book for this literature? Any reference book? Did you provide in the write-up or something?
For
Book for this literature for the PPT.
for this
Yeah.
lecture, I
Yeah.
have given the reference.
Yeah, you have given the reference. Yeah. And one question from Ipsita, I didn't get the question properly. Why only K term, not I and J? Why only K?
Yes, I think she was asking the question for slide number 11.
Okay, just let me see.
Wow.
I just noted down. So
Wow, great.
Where?
slide number 11, the top equation you
Shall
have
I
written.
share it?
Yeah, if you can, sir. Yes.
Okay, just 1 minute. This one? No.
You didn't share actually. Your
I am
screen
not
is
shared?
not shared. No, your screen is not shared.
Okay, just 1 minute.
Yeah. Now it is shared.
Yeah, yes. Same one, sir. Geostrophic approximation.
So
Ah,
I repeat the question.
huh.
Why only K term, not I and J?
Where?
Why only K term? I think the first one then.
No. These are the two equations for the horizontal velocities. Okay, horizontal component of geostrophic velocity speed. So these two equations I am trying to write by a single equation.
That call, yeah.
Okay, so I have to take the cross product with K.
Yeah, maybe that cross product part is not very clear for her.
That's what I was telling. Okay, that I am explaining again. So now this grad P, this is del P del X I plus del P del Y J. Okay, so if I take the cross product, then only I will get the two components in the horizontal direction. So K cross I will give us J, and K cross J will give us minus I component. So if I take the cross product with K, then only I will get these two horizontal components. Is it the question?
I hope so, but we cannot do the interaction.
Or is she asking that whether why that for phi geopotential height I have kept K?
Both are same. Okay, you can give it or we can skip it because the question is not that much clear.
Okay.
Or maybe see, you're referring to the next slide where you have defined the pressure gradient.
Yeah, the first one, the first.
Next slide.
Go to the
next
next slide, the first one.
Right.
The
Yeah.
first
Here,
one.
here
Yeah.
the Ij is there, but K is not there because it's a horizontal pressure gradient, not a vertical pressure gradient. Del P
Yeah.
is equal to.
Acha, here, no, but her question is why only K? So this is the horizontal pressure gradient. So
Yeah.
del phi del xi, del phi del yj. So I am taking cross product with K. So K cross I if I give, so then I will get positive J. So our V will be equal to 1 by rho F del phi del x. So that's what our previous equation. If
Yeah,
V is equal to 1 by rho del phi del x.
okay, let's wait if you put another questions, but I think it is a issue of vector cross product only. So, and the another is, can we explain a storm condition by means of this hydrostatic model?
See, storm condition, it depends on what type of storms, okay, by hydrostatic models. So if it is a very small scale, in our mesoscale modeling, we tell that if the vertical scale and horizontal scale is comparable or vertical scale is larger than the horizontal scale, then only hydrostatic approximation we cannot use. Otherwise, we can use. If it is large scale, so then it is used. For that only I was telling, if it is tornado vertical scale is very large compared to the horizontal scale, or maybe they are comparable. So then the hydrostatic approximation will not be valid. So then we have to use, in modeling, we have to use non-hydrostatic model.
Okay, there is a big question from Rohan Mandal, and before coming to that question, let's ask small two questions. One from Ratna Vira. Is virtual temperature used when water vapor is present?
Yes.
If so, can we use the gas constant of dry air?
Yeah, virtual temperature we are using because we are using the gas constant of dry air. Virtual temperature we are using so to take out from this on the means so that R will not be different.
Yeah. So why do we need hydrostatic balance? That philosophical part.
Why?
Why do we need hydrostatic balance?
It becomes easier for us to calculate. Just from modeler's point of view, I will tell one very good reason is that hydrostatic balance is that it eliminates that, it filters out the vertical sound wave, vertically moving sound wave, which is a noise in meteorology, which is meteorologically insignificant, but it is very noise. It creates noise. So vertically moving sound wave we can yeah. And and another thing is that it is not the equation which should be used to calculate W, because I told that it is the difference. W is the dW dt. It is the difference between the two large terms. So W we can find out from some other equation.
Yes.
So it is easier to use.
Yeah. Sir, while explaining the geopotential equations, you have mentioned the concept of virtual temperature. Sir, can you tell why we use in the calculation of CAPE or in the potential of severe storms instead of normal temperature, and why is it so much important in meteorology instead of the normal temperature term? Okay, the main question is that why virtual temperature is important than the normal temperature.
Because moisture plays important role in these terms, and effect of moisture we cannot ignore. So to include that effect of the moisture, because moisture is the main agency which transfers energy from one layer to another layer, okay, in the form of latent heat. So we have to include the effect of the moisture in that model. So if we want to include the effect of moisture instead of temperature, we have to use virtual temperature.
Thank you. I think this should be the last question maybe. Is it possible to simulate the different types of winds like geostrophic wind in a wind tunnel in the lab to prove it?
In the wind tunnel in the lab, I don't know, maybe possible. Somehow we have to.
It is not part of this lecture today. So
Yeah, we have to eliminate the effect of other forces.
So I think the question answer part is done, Dr. Rohini.
Thank you, Dr. Swagata. So, sir, please can you unshare your screen?
Okay.
So, before we go to
Sorry,
vote
sorry.
of thanks, I would like to mention the today's statistics. Around 211 participants have participated in today's lecture as of now, and 176 have rated it as excellent and very good. So thank you, sir. This was very nice lecture series with a good discussion on for the lectures. So you have sent questions for us, and do you want us that the convective part should be an assignment for the participants?
It is written there, na?
In the fifth one, the questionnaire.
Yeah, for that only I have not discussed it in it.
Okay,
So
so
I
we
thought
will
that-
share that particular thing with them.
Yeah. So
As
it can be taken as that one short question Sumesha sir told to give, na? So that can be the short question.
Okay, then we will be sharing it, emailing them so that they can do the assignment and submit it.
Yeah, let me just clarify it. Can I?
Yeah.
Am I audible?
Yes, sir. Please share the screen. I will.
Yeah, am I audible?
Yes, sir.
Yeah, you are audible, sir.
Oh, okay. Well, actually, I just want to say to all the participants that many people have given us suggestions and feedback that this lecture series on dynamic meteorology or atmospheric dynamics should also have home assignments. Like every lecture should have a home assignment given to the participants. And in the home assignments, what we discussed or what we thought is that there will be 10 marks total and 5 questions approximately. One question will be a numerical problem based upon the lecture of that day. The second question will be like a short question with a short answer, descriptive answer. And there will be 3 multiple choice questions, right? So accordingly, Dr. Sarkar has already shared or set the questions for the participants. All the participants will be given this home assignment and they need to submit the answers before the next lecture. That means the next lecture is on next Saturday, that is on 8th of March. So all of you must submit the home assignment before or by 7th of March, okay? And you will get the whatever score based upon your answers. Obviously, you can listen to the lectures once again. You can refer to the books which has already been given by Dr. Sarkar. And so it will be like an open book examination for you. The marks, 10 marks, which is set for these questions, will be counted also in your final test. For example, all the home assignments of all the lecture series, all the lectures, we will calculate finally the 25% of those scores that you will get will be counted in your final test. So the final test will have 75% marks and 25% marks will be based upon your answers of the home assignment. I hope I'm clear. If not, we can explain the same things to all of you by email also, the instructions and the procedures. Okay. The reason why we are doing is that just conducting the examination at the end of the lecture series after 4 months or 5 months, probably you may not be benefited much that way. Rather than that, if you are able to concentrate on every lecture seriously and then read the books also accordingly, probably you will learn better about its practical applications, and also you will have a deeper understanding of the subject. So that's why we thought that we better give home assignments for every lecture, and all lectures combined together will have 25% weightage, and the final test will have 75% weightage. I hope I am clear. And Dr. Rohini will share the home assignment with all the participants by email. Dr. Rohini, you will share it by
Yeah.
email?
We will send the email on Monday because today our team is on leave. I mean, they have holiday. So
Monday, if you are sending today, Saturday, okay, but then they will get less chance, less time. Like we are giving them 7 days for submitting the answer.
yeah, because today is first Saturday, so we have holiday here. The non-teaching staff is on holiday, so we cannot send. They have to send it, and they don't work on Saturday, Sunday, sir. So we have to wait till
All right,
Monday.
so I think 5 days should be sufficient, I hope.
Yeah,
For
I
all
think
the,
it's fine.
and
Yes.
because this is open book examination, they can
Exactly.
listen to the lecture once again on the YouTube, which will be archived, and refer to the books, and then answer only 5 questions. 3 of them are objectives. One is a numerical problem, and
Sir, but will it not be difficult to check the numerical problem from
no, it
more
will not
than
be difficult.
250?
I think Dr. Sarkar, it will be okay, right? We will send you the
250
answers to all the
participants,
questions.
sir. At least.
Well, let us see how many of them. And most of these numerical problems are based upon the textbooks. Generally, most of the textbooks give the numerical problem and also the answer there. If you read it carefully, you will find the answer in the textbook itself. Right?
Truly speaking, I think Rohini raised the point. Maybe Dr. Sarkar can do that, but a lot of others who are in a really every day in a busy schedule, I'm little doubtful. That case, MCQ would be the better one.
Then that case, what?
MCQ.
MCQ.
What do you want to tell? I don't have any work.
No, sir.
No,
Dr. Swagata, I don't think.
Yeah.
No, you are very particular on your task. That's why. That is, and there are no other things.
If it is difficult for Dr. Sarkar to evaluate it depends on how many of them really submit the answer. Suppose all 250 participants who are present today, or how many participants
I
are
think
present
let's
today?
make it little clear. The final one will give the grade certificate. This individual one who will submit, will also do another type of appreciation, I think, because if we really want to take 25% of that, then in the final score, it may affect a lot. The number of participants may decrease.
The reason we are giving the weightage for this.
But anyway, by that time, we can stop the YouTube and we can stop the recording.
First, let's first have vote of thanks and then we can have a quick discussion on this. Okay, sir. Someshwar, sir, okay?
Yeah, fine. Yeah, deliver the vote of thanks, and then after that we can
shut
down
go ahead.
YouTube and then discuss it.
So I request Ms. Mrunal Naik from IITM to please conduct vote of thanks. Mrunal, please go ahead.
Yes, ma'am. Can you please share the screen?
Yeah, I'll share the screen. Yeah, Mrunal.
Yeah. So on behalf of organizing committee, I would like to thank each of you for contributing on the 7th lecture of the weekly online lecture series on atmospheric dynamics and its application in climate science. Firstly, I would like to thank Dr. Q O, a DG, DMH Manma for giving a welcome address and brief information about this lecture series. My deepest appreciation goes to our speaker of a day, Dr. Abhijit Sarkar, scientist F, retired NCMWRF, for delivering a very informative lecture on hydrostatic balance, geopotential, use of pressure as a vertical coordinate, ageostrophic wind and horizontal acceleration. I also thank Dr. Rohini Bhavar for moderating today's session and Dr. Swagata Praya for managing a question answer session. I also want to thank all the panelists and EC members for their guidance and constant support for every minute detail. I extend my thanks toward all participants and attendees who joined us from across the globe. Last but not the least, sincere thank goes to the team member of Savitribai Phule Pune University involved in organization of this lecture. Thank you, everyone.
Thank you, Mrunal. So today's lecture is over, and the next lecture will be, I will just,
Professor
by
Bhaskar Rao.
Professor D.V. Bhaskar Rao, sir, from Andhra University, which is on 8th March, and it will be on vertical variation in geostrophic wind, thermal wind, barotropic and baroclinic atmosphere. So thank you, everyone. And
Thank you.
let's stop.